Okay. Yeah. Welcome everyone. So on the board, on the first board here is kind of the rough plan for this session. I actually haven't timed myself, so let's see how far we go. I think the main goal is to introduce or at least refamiliarize, sort of kind of bringing sort of long lost memory in this brick back to cache of kind of statistical procedures that is taught in, say, in a sort of a statistics 101 course, but then sort of also on the way point out some maybe assumption that was never clarified in those kind of courses. Okay, so true to a statistics 101 course, we're going to do a flop coin flip. What's a good pointing color? Okay, red. So this will be our task. So our task will be to estimate the probability of coin toss coming out head, because this is a Bernoulli sort of a Bernoulli random variable. We only need to specify sort of what is the probability of head, and let's call that just so that everyone starts getting used to the notation that we're going to use throughout the seminar. I'm going to call that W because it's going to be a parameter. So that's going to be the thing that we want to estimate. And along the way, we shall introduce what are the possible ways to do such a statistical inference. We'll be introducing model parameters and something called the likelihood functions. And we are going to use, just for today, something called the maximum likelihood method. Actually, because in this case, we don't actually have a lot of degeneracy. Actually, we don't have degeneracy depending on the model that we construct. And for such situation, we actually have that the maximum likelihood method is in some sense the best, in some specific sense that we'll talk about. And just a bit of preview is that we are going to point out that, or just state explicitly that whatever inference method we use to predict the probability, that inference method itself produce so random results, because the inference depends on a set of data points, previous observation about the coin toss, for example, and therefore it is the result is itself random. And the need to quantify this randomness and is important because we need this quantification to tell us how good our inference method is on average. And that will hopefully lead us to some important concept that we will define later on. Okay, let's start. Do any sort of questions before while we are moving to another board? Let's move to the next board. If there's no question, let's start. Okay, I'm now on the next board.
The orb hasn't quite moved yet.
Dan?
Maybe move closer to the board, maybe?
I think Dan is still controlling the orb.
Oh, is he the speaker?
Uh-huh.
We need to all push him.
Can the orb see the second board? Not really.
Oh, the recording can't see it is the problem. Until the
right. By the way, the supplementary session is supposed to be more informal, so please interrupt me when
oh, there we go.
Whenever you want.
That was back.
Sorry, I was away from the computer and I got caught.
Sorry, I moved to the second board rather quickly.
Yeah, good.
We were trying to push you over there.
Oh yeah, that was an amusing experience. Anyway, I'm glad to oblige. Okay, sorry to interrupt. You go along.
No, that's okay. Okay, so let's start. So the situation is that I'm going to imagine an actual situation where someone, a person, is on the other side of the room tossing a coin, tails, heads, and then he is sending, say, by a mailbox or something, out a set of n observations. So maybe there's heads, tails, heads, 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 or something like that. There's n of those. So we call that that set of observation a data set, and I'm going to use this notation and subscript n for the size of the data set. So each observation is going to be a random variable, in this case a Bernoulli random variable, standing for each is either, so each one of these is either flipping out heads or flipping out tail. Hopefully I'm better at projective geometry than I'm at perspective drawing. Okay. So our task is to come up with an estimate. I'm going to use hat for anything that is an estimate of so basically the person is asking you, if I flip this coin again, what is your estimate? So how much would you bet that this is hat? How much would you be willing to bet? And that's a kind of function of your probability estimate. So this is a problem with some money on the line. So we can have a rather stupid method. So a stupid statistical method. Let's call that method 0. And just ignore all the previous data and just guess. P probability of turning out heads is half, and therefore the probability of turning out tails is a half. So this only works for the fair coin. Like there's only one kind of coin in the world that where this method will work. Like if the person is nefarious and just do use a loaded coin or something like that, then this method would never work. So a more common method, the one that is taught in Statistics 101, would be setting out a model. So assume that so if we kind of we can argue like this: if we assume that the probability of landing heads is equal to some number omega, and this omega, because it is a probability, lies in this interval 0, 1. So already this is some concept that will be important for us. So this will be called a parameter, and this is a parameter space that will frequently label just capital W. So this is a very simple parameter space. So if we assume that that is true, under this assumption, then the probability of, we can ask, what is the probability of, why is there a line? Okay. What is the probability of observing, of observing this data set given this assumption? So this function, so we are thinking of this dn as a data set fixed by that person, right? So we are only ever going to get this data set dn. It's fixed, and this is a function going from, this is a function of W. And this is called the likelihood function. So this is the probability of observing Dn given W, or assuming that we the probability of heads is W. Okay. Let me maybe not move to another board. Let me just erase the pictures and first give the form of this likelihood. So I hope that you can agree that if I have the likelihood of a sequence, say the following sequence, head, tail, head, tail, tail, the likelihood that it happens exactly like this is, well, the likelihood of landing heads the first time is W, assuming that it is the likelihood of landing heads W. Then tail is 1 minus W, and W 1 minus W, and 1 minus W. And if you are assuming that each of these is an independent throw, it's a different throw, and the person doesn't get tired after a while or something like that, so that the condition of the throw is all the same, then the probability of this particular sequence is just multiply all this together, which means the probability of the particular sequence is just given by multiplying this many W and multiply this many 1 minus W, where H is just a number of heads and T is the number of tail. And because this sequence is of length n, T is just T is just equal to n minus H. Okay, but just for later convenience, just so that later I don't need to sum over all possible sequences, I'm going to write this likelihood of observing this this set of data as an unordered set. So the order doesn't matter. So there is an n choose H factor out the front. So that's just the binomial distribution. So this is equal to n choose H W to the H 1 minus W to the T, and the likelihood is just the binomial expression. Okay, so let's move to the next board. Yep, that's clearing board. Okay, so before I go into the details of that estimation, that model, I'm going to propose another model method 2, where this is kind of a more complex model and might answer some of the questions just now regarding degeneracy and singularity. Is that we don't believe that that person is being fair to us, even though he gave us a sequence of heads and tails. He might be using multiple different coins. Say maybe you guess that he is using 2 coins. Maybe there is he has a box. Inside a box there's 2 coins. One of them is a fair coin. One of them is biased. And he is every time he throws a coin, he's actually reaching into the box and randomly picking out one of the coin with some probability, say T. In which case you will have the probability of landing heads is given the probability T of picking a coin and the bias W of the bias coin. The fair coin is just a half. for probability of landing heads, then the likelihood function becomes a function of two variables. And it's equal to, well, it's if it choose with probability t, it choose the fair coin, in which case the probability of landing heads is a half. With probability 1 minus t, it choose the bias case, bias coin, in which case the probability of landing heads is 1 minus w. So you might well use this model and observe some degeneracy. If for some reason w is a half, then this model sort of collapses back to the original model because both of these coin are fair, so it doesn't matter which one you take out. So this is an example of degeneracy, and an example in which you might have reason to believe that someone is using a more complicated world, is inhabiting a more complicated world than you imagine. So we won't be looking at this at the moment in the interest of time. I'm just going to dive into the method one just now and tell the story of how people usually do statistical estimation in that situation. So the method that I'm going to introduce is going to call maximum likelihood estimation. So we have the likelihood function just now. The idea is to treat this function like an objective function. In what sense can we justify that? Well, this is a bit of a mental gymnastic where you assume that the truth, say, the best parameter in your set of model is the one that is the most likely to produce the data set you observe. To label the truth W0, we don't actually know that this is an assumption. This is the realizability. Okay, so we are going to use maximum likelihood estimation, and so due to time, I'm going to skip all the actual optimization. But some important concept to note is that we usually don't actually do maximization on this function. Sorry, I was actually saying that W0, the fact that W0 exists, meaning the truth, the assumption that the person is actually using one coin and that coin has a fixed probability of landing head. This is the realizability assumption that Dan was talking about just now. Okay, so with that assumption, this model attempts to say that the best estimator we can get that is closest to the truth will be the one that maximizes this likelihood function. So we don't actually in practice maximize the likelihood itself. We actually maximize the log of the likelihood function because of numerical stability and because the calculus is easier to do. And log is a monotonic function, so maximizing one is the same as maximizing the other. While I'm here, I'm going to introduce also another quantity very much related to this likelihood function called the empirical KL divergence, or the empirical training error. So this quantity is actually given by oops. sorry, I think there was a minus. Where this thing is, where for now this is the entropy of the true distribution, and we don't need to talk about what that is for now. It is just something that is that doesn't depend on W. So maximizing this thing is the same as maximizing the log of this the likelihood. It's the same as minimizing, because of the negative sign, this quantity. And the expected value of this quantity is equal to something we call the KL divergence, and it's equal to so if the truth is at W0, is equal to this expression. And it's usually denoted with K. This is integral with respect to dx. Okay. We will talk about this a lot more next week. But so if you want to, so let's go ahead and maximize this. If you try to go and find the arg max over W in 0, 1 of this, well, you might go ahead and differentiate this function and find where the gradient vanishes. And if you solve the equation, you get something like the estimate that you're trying to find. The estimate that makes the gradient vanish is equal to 1. Let's call that W hat, which is the estimate. Satisfy this equation. So if people recognize this is the odds, so odds is just another way of encoding probability. You say 2 to 1 instead of probability between 0 and 1 is equal to the ratio of heads to tail. And this implies that the W hat is equal to the number of heads divided by the number of data, which is something that everyone sort of already know from the outset, which is the best guess of what the next coin toss would turn out head would just count the number of heads divided by the total number of throws, which is the frequency of heads. Something to note though is that there is some issue in this equation when for the solution when h is 0 or h is equal to capital N, in which case you get W hat is equal to 0 or 1. We will see what problem that causes a little bit later on. Sorry, then is it okay if I just continue for another 5 more minutes?
Yeah, sure. Go ahead.
Let's move to the other board. Thank you. So we get this formula of the maximum likelihood estimate, this procedure. So this procedure of observing dn and then counting number of heads and then computing W hat equal to H on H equal that H on N, and then finally predicting the probability of head, the goal that we actually want to get at the end is just equal to the probability just now evaluated at this estimate. This procedure turns out with something that is that depends on how many heads there are in the data set. So this quantity here is actually a random variable of the is a measurable function of the data set, and therefore it's itself random. So to know if to know if how well this procedure will work. So before you even go into the room and observe the data set, we know that a different data set, even though that person is using the same coin every time, a different data set will give you a different estimate W hat. So think about the case when the person is mean and only give you 2 toss. And in that 2 toss, it might be both heads, in which case you will estimate your probability of the next. According to this procedure, the probability of next coin toss landing heads will be 1, because there will be n on n equal to 1. And I don't think you will be very confident about that that estimate. So we want to, so this is part of what it meant to have a statistical learning theory, is to quantify the performance. So let's write it down. Statistical learning theory. Oops. Then it is sometimes the. Okay, so I was saying that the role of statistical learning theory is to quantify this uncertainty of any inference procedure, so that you know that when you use this inference procedure for a different data set and for possibly different truth, so a different data generating process, you know how well this inference procedure will work. So for our case, I'm going to sort of, without showing the calculation, I can post the calculation later. I can tell you that for this maximum likelihood procedure, so if the truth is given by that assumption that we make that the person is throwing a single coin with a fixed probability of landing heads of W0, then the distribution, remember the fact that W hat itself is a random variable, the distribution of the W hat is given by, well, it's given by what is the probability of you estimating H on N? What is the probability of us estimating that? Well, that's the same as the probability of having H heads in N trials. So that's again the binomial distribution, but this time with the truth, assuming that it is W0. So one thing from, say, elementary probability that we shall use without comment here is that there is this very famous normal approximation. So using normal approximation to binomial, we know that if we have a really large data set, then we have, so this is W hat. And if we plot the histogram of W hat, it's going to look like, it's going to be well approximated by a normal distribution centered at W0. The fact that this is centered at W0 is another statistics concept that we'll be using, which is called, this is an unbiased estimator, meaning on average, you actually expect that your estimate calculated like this is going to be the truth. The expected value, the on average part of that is kind of important. And the spread here, given by the variance of the normal distribution, is given by well, it's given by the variance of this distribution, right? In this case, we actually have exact formula, and if you calculate that using the binomial distributions variance, you get this. So W naught multiplied by 1 minus W naught divided by N. So notice something though. This distribution, so notice that this normal approximation only holds when n is really, really large. So what happens when n is really, really small? So if n is really, really small, like 1 or 2, then your normal approximation has a very large variance. So this sigma square is very is large, is on the order of 1 of the number 1. In which case, remember that the normal distribution does not confine itself to 0, 1. So this is actually a really, really terrible approximation. Particularly, it's even worse when the truth, W naught, is very, very close to the two problematic points that we're talking about before, which is 0 and 1. So, for example, if W naught is very, very close to 0, then you need a lot of data before the normal distribution concentrates around that point and not have something like this happening, which is nonsense because W0, because your estimate should never be below 0. Okay. So this spread, this thing, this is a phenomenon that the fact that we have a normal approximation to the binomial distribution, to the distribution of our estimator here, is kind of a general phenomenon called known as asymptotic normality. Okay, and because I have run out of time, I'm just going to say that the generalization of this phenomenon to, say, arbitrary dimension model and to different inference procedure is use something called the Fisher information matrix. And then I'm just going to mention the intuition here. So just now, if we remember the method that we were using just now, where we are looking at log of the likelihood function. So if we plot this function between 0 and 1, it could be that we are unfortunate and have a very have a profile like this, or we could be fortunate and have a profile like that. In the second case, in this case, if you nearby estimates of W, so if your data set is somehow a little bit different, and causes you to estimate not the true W but a little bit to the left or to the right, it sort of influences the likelihood function a lot, and you would you will see that you will see something is wrong, and you want to push yourself to the correct direction and towards that maximum point. Meaning the maximum point is very, very sharp. In this case, though, the maximum point is nearby models are like it, are very much not much different from it in as far as the likelihood function can tell. In which case, the spread of your distribution, the normal distribution, the asymptotic normal distribution that you have will be fatter, and in which case you have less confidence about your estimate, and that the measure of the sharpness, or actually the curvature near your estimate, is called the Fisher information. Sorry, I went way over time. Dan, I think I will stop here. I will post my written notes instead.
Yeah, that's awesome. Thanks, Edmund. That was a really great line from coin tossing to the Fisher information. Thank you.